Welcome back to Axial Deformation Examples. In this example, we look at calculating the deformations in a segmented bar where the force through the bar is the same in all segments. This picture shows the example that we're looking at. You can see that all the information is given, and each bar has a different area and a different elastic modulus and a different length. As mentioned, the force in each bar is the same because if we do a cut anywhere in this system, we would find that the force has to be equal to the applied force of 350 kilonewtons. So let's go ahead and write that down as a given. In addition to all the information that is shown on the picture, we are also given that the internal force in each bar, F1 equals F2 equals F3 equals 350 kilonewtons. Okay? And we are asked to find the deformation in bar 2 and the total elongation or rightward movement of the assembly. So there are two slightly different things. Deformation in bar 2 would just be the deformation or the elongation across this bar, and I would call that delta 2. Okay, and each as the bar moves to the right, each of these points at the ends of the segments will also move to the right. We can calculate any of those. We're asked to calculate the rightward movement at the end of the assembly, which is point D, and I could actually draw that. Say maybe the whole thing moves over that far. I would label that V sub D. So that's the total rightward movement at the end. So let's look at how to calculate these two separate pieces. We desire the best because we expect them to be small quantities. We want to calculate these deflections in millimeters. Considering the units we are given for this problem, force in kilonewtons, elastic modulus in gigapascals, areas in millimeters, we can work with, without having to do any conversion, we can work with kilonewtons, millimeters, and gigapascals. Remember that 1 gigapascal is 1 kilonewton per millimeter squared. So the only conversion factor we have to worry about is that for the length, which is given in meters. It's a fairly easy one, recognizing that 1 meter is equal to 1 times 10 to the third millimeters. So that is the only quantity that we'll need to convert, and it's good to think about that in advance of starting the problem. Okay, so start out by evaluating delta 2. Remember, deflection in any segment can be evaluated by FL over AE. So let me write that. Delta 2 equals F2 L2 over A2 E2 equals 350 kilonewtons. Force is the same in every segment. The length of segment 2 is 0.4 meters. I'm going to convert that to millimeters by multiplying by 10 to the third, divided by the area of segment 2, which is 6,000 millimeters squared, divided by the elastic modulus of segment 2, which is 105 gigapascals. And this, when we punch these numbers into our calculator, 0.272 millimeters. Remember, I don't want to carry out too many significant digits, which would be more accuracy than I know this answer to. So that's one of the answers we're looking for. The second one, V sub D, the end deflection, we can calculate simply by adding up the deflection in each of the segments. So V sub D equals, it's like a delta total, delta 1 plus delta 2 plus delta 3, which is F1 L1 over A1 E1 plus F2 L2 over A2 E2 plus F3 L3 over A3 E3. So as I do this calculation, one of the things I recognize is that F1, F2, and F3 are all the same. I can pull that quantity out in front. That's not always the case, but it is the case here. Okay, and writing everything else down, L1 is 0.8 times 10 to the third millimeters divided by 8,000 millimeters squared times 200 gigapascals plus, for segment 2, which we already calculated, 0.4 times 10 to the third millimeters. I notice this should be written as millimeters up there as well. 6,000 millimeters squared times 105 gigapascals plus finally segment 3, 1 times 10 to the third millimeters divided by 2,500 millimeters squared times 150 gigapascals. And if we punch those numbers into our calculator, we would get the answer 1.33 millimeters, which is the total deflection. So our deflections in units, they are small quantities. V sub d, the end deflection, quite a bit larger than the deflection in segment 2, which makes sense because segment 3 in particular is long and thin, and so it's going to have a larger deflection. Our kind of logic check checks out, and we're done with that example.